Imagine two objects in space. Both are roughly 12 miles across. Both weigh more than our entire sun. Both are made of the same impossibly dense material. And yet, one flashes like a cosmic lighthouse, sweeping beams of radiation across the galaxy with clockwork precision. The other erupts without warning, releasing more energy in a fraction of a second than our sun produces in 100,000 years. A third sits almost invisible, quietly cooling in the darkness, detectable only if you know exactly where to look. They are all neutron stars, the same kind of object. And tonight, we are going to discover why one of the most extreme things in the universe can wear so many different faces, and how a single neutron star can transform from one type into another over the course of its lifetime. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Picture the aftermath of a massive star's death. A cataclysmic explosion has just torn the star apart, scattering its outer layers across light years of space. But at the center of all that destruction, something has survived. An object so dense that a teaspoon of its material would weigh billions of tons on Earth. An object smaller than most cities, yet more massive than our sun. A neutron star. You have almost certainly heard this term before. Neutron stars show up in documentaries, in textbooks, in conversations about the most extreme objects in the universe. But here is what most people do not realize. When astronomers study neutron stars, they do not find one uniform type of object. They find pulsars that flash with clockwork precision. They find magnetars that erupt with devastating bursts of radiation. They find faint, quiet objects that barely emit any detectable signal at all. They find neutron stars being spun up to dizzying speeds by companion stars. And they find others that exist for only fractions of a second before collapsing into black holes. These are all neutron stars, the same fundamental type of object, and the reason they appear so different from one another comes down to a handful of physical properties. How fast the neutron star is spinning, how strong and how organized its magnetic field is, how old and how hot it is, whether it has a companion star nearby, and whether its emissions happen to be aimed in our direction. Change any one of these properties and the same neutron star can look like an entirely different beast. More than that, these properties change over time. A neutron star can begin its life as one type and evolve into another. It can belong to two categories simultaneously. The labels astronomers use, pulsar, magnetar, millisecond pulsar, X-ray source, are not names for separate species. They are names for different states, different snapshots of what is fundamentally the same kind of object at different moments in its existence. Tonight, we're going to walk through every major type of neutron star that astronomers recognize, not as a disconnected list of definitions, but as a single continuous story about how one object, born in one kind of event, can appear in so many different forms depending on spin, magnetism, age, temperature, and environment. And we are going to begin at the very beginning with the violent moment that creates a neutron star in the first place. Every neutron star begins with the death of a massive star. Not every star qualifies. Our sun, for instance, will never become a neutron star. It simply does not have enough mass. When the sun exhausts its hydrogen fuel billions of years from now, it will swell into a red giant, gently shed its outer layers into space, and leave behind a white dwarf, a hot, dense remnant roughly the size of Earth. A white dwarf is held up by a quantum mechanical effect called electron degeneracy pressure, where electrons resist being squeezed too closely together. That is enough to support a stellar core up to about 1.4 times the mass of our Sun. But stars born with roughly 8 or more times the mass of our Sun face a fundamentally different ending. These massive stars burn through their nuclear fuel in stages, fusing lighter elements into heavier ones deep in their cores. Hydrogen fuses into helium. Helium fuses into carbon. Carbon into neon. Neon into oxygen. Oxygen into silicon. And finally, silicon fuses into iron. Each stage releases energy that keeps the star inflated against the crushing inward pull of its own gravity. But iron is the end of the road. Fusing iron does not release energy. It absorbs energy. So when the core of a massive star fills with iron, the engine that has been holding the star up for millions of years suddenly shuts off, and the core collapses. What happens next unfolds in less than a second, and it is one of the most violent events in the known universe. The iron core, roughly the mass of our Sun and about the size of Earth, collapses under its own gravity at speeds approaching a quarter of the speed of light. In a fraction of a second, it goes from being thousands of miles across to being roughly 12 miles across. The compression is so extreme that protons and electrons are forced together, merging into neutrons. The core becomes a ball of neutrons packed shoulder to shoulder at densities that stagger the imagination. A single sugar cube-sized piece of this material would outweigh every building in a large city combined. The collapse halts when the neutrons themselves resist further compression. This resistance comes from two sources working together. The first is neutron degeneracy pressure, the same quantum mechanical principle that supports white dwarfs, but now applied to neutrons instead of electrons. The second is the strong nuclear force, one of the four fundamental forces of nature, which becomes powerfully repulsive when particles are forced too close together. These two forces create an almost incompressibly stiff material, and the collapsing core slams into this wall of resistance and bounces. That bounce sends a shockwave outward through the rest of the star. The shockwave, aided by an enormous flood of ghostly particles called neutrinos, tears the star apart from the inside out. The outer layers are blasted into space at thousands of kilometers per second in a supernova explosion. For a few weeks, the dying star can outshine an entire galaxy, hundreds of billions of stars, all outshone by the death of one. And at the center of the expanding wreckage, spinning rapidly amid the chaos, sits the newborn neutron star. This is where the story of neutron star diversity truly begins, because the neutron star that emerges from this cataclysm is not a blank slate. It is born with a specific set of physical properties, and those properties determine everything about what kind of neutron star it will appear to be. First, mass. Most neutron stars fall somewhere between about 1.2 and roughly 2.1 times the mass of our Sun. The exact mass depends on the original star's core, and on how much material falls back onto the neutron star during the explosion. There is an upper limit. If the remnant's mass exceeds roughly 2 to 2.3 solar masses, not even neutron degeneracy pressure and the strong nuclear force can hold it up, and it collapses further into a black hole instead. Neutron stars exist in a narrow corridor of mass, too heavy to be white dwarfs, too light to be black holes. Second, size. Despite containing more mass than the Sun, a neutron star is astonishingly small. Its diameter is roughly 20 kilometers, about 12 miles across. You could fit a neutron star comfortably within the boundaries of a mid-sized city. If you could somehow place one next to Earth, it would look like a marble beside a basketball. This combination of enormous mass and tiny size creates the most extreme conditions found on any stable object in the universe. The surface gravity is roughly 200 billion times stronger than Earth's gravity. If you could somehow stand on the surface, you would be flattened into a layer of atoms thinner than a sheet of paper. An object dropped from a height of just 1 meter above the surface would strike the ground, traveling at roughly 7 million kilometers per hour. Third, spin. When the core of a massive star collapses, it conserves angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in close. The original stellar core might have been rotating lazily, once every few days or weeks, but when it collapses from thousands of miles across down to just 12 miles, that lazy rotation becomes ferocious. A newborn neutron star can spin anywhere from a few times per second to dozens of times per second, depending on the dynamics of the collapse and how much angular momentum the original core carried. Fourth, and this is perhaps the most critical ingredient of all, the magnetic field. Stars have magnetic fields, and when the core collapses, those field lines are compressed along with everything else. A magnetic field that was unremarkable in the original star becomes extraordinarily powerful inside the tiny neutron star. A typical neutron star is born with a magnetic field roughly 1 trillion times stronger than Earth's. Some are born with fields 100 or even 1,000 times stronger than that. The exact strength and structure of this magnetic field will turn out to be one of the most important factors in determining what kind of neutron star astronomers observe. Mass, size, spin, magnetic field. These are the 4 ingredients. The recipe that determines a neutron star's behavior depends on how these ingredients combine, interact, and most importantly, change over time. Here is something that might surprise you. When most people hear the term neutron star, they immediately think of a pulsar. That famous image of a rapidly spinning object shooting beams of radiation into space. Pulsars are indeed the most well-known type of neutron star. But most neutron stars are not observable pulsars, not even close. Consider the numbers. Our galaxy, the Milky Way, has been producing neutron stars through supernova explosions for billions of years. Astronomers estimate that the Milky Way contains somewhere around 1 billion neutron stars, possibly more. Yet we have detected only a few thousand pulsars. That is a tiny fraction of the total population. So where are the rest? Most of them belong to the most common and least dramatic category of all. Ordinary, isolated cooling neutron stars. This is the baseline population, the default state, the category that receives the least attention but almost certainly contains more members than every other category combined. An ordinary cooling neutron star is exactly what the name suggests. It is a neutron star that was born in a supernova, received its initial spin and magnetic field, and is now simply cooling down over time. When a neutron star first forms, its interior temperature can exceed 100 billion degrees. That is thousands of times hotter than the center of our sun. But neutron stars do not stay that hot. They radiate energy away, first through neutrinos escaping from their interiors, and then through photons radiating from their surfaces. Over thousands and then millions of years, they gradually grow cooler and fainter. A young, cooling neutron star might still be hot enough to glow in X-rays. Its surface temperature could reach 1,000,000 degrees or more, meaning most of its energy comes out as X-ray light. But even that X-ray glow is relatively faint. With our best space-based X-ray telescopes, we can only detect these thermal emissions from neutron stars that are relatively close to us in cosmic terms. A cooling neutron star sitting on the far side of the galaxy would be essentially invisible. As the neutron star ages further, it cools below the threshold where it emits detectable X-rays. After a few million years, it becomes extraordinarily difficult to observe by any method. It is still there, still a ball of matter denser than an atomic nucleus, still hurtling through space at whatever velocity the supernova kick gave it. But it produces no beams of radiation, no bursts of energy, no dramatic signals of any kind. It is dark, silent, and to our instruments, effectively non-existent. This is why astronomers believe there are far more neutron stars in the galaxy than we will ever directly observe. The detectable ones, the pulsars and magnetars and X-ray sources, are the tip of the iceberg. Beneath the surface lies an immense, quiet population of cooling objects drifting invisibly through the galaxy. Objects that may once have been active pulsars or even magnetars, but have long since exhausted their rotational energy or magnetic activity and now simply coast through space, slowly cooling toward the background temperature of the cosmos. This quiet population forms the baseline from which all other types emerge. Every other category of neutron star we are about to explore is essentially one of these objects caught at a particular moment in its life, doing something that makes it visible and scientifically interesting. The pulsars, the magnetars, the accreting X-ray sources, all of them will eventually join this silent majority. Understanding the baseline helps us understand everything else, because it reveals the default state. The real question for every other category is not what is this object, but rather what is making this particular neutron star different from the quiet, cooling default right now. The most famous answer to that question is rotation. And this brings us to the best known category of neutron star in all of astronomy, the rotation-powered radio pulsar. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope at Cambridge in England. She was studying something entirely unrelated to neutron stars. Her project involved observing how radio signals from distant sources are scattered by the solar wind. But buried in her data, she noticed something strange. A signal that pulsed with extraordinary regularity. It flashed on and off every 1.337 seconds. Not roughly every 1.3 seconds. Not approximately. Precisely 1.337 seconds. Every single time, like a metronome. The regularity was so perfect that for a brief, exciting, and slightly unsettling moment, the research team genuinely considered the possibility that they had detected a signal from an intelligent civilization somewhere in space. They even gave it an informal label, LGM-1, short for Little Green Men 1. But when more of these pulsing sources were discovered in different directions across the sky, the extraterrestrial hypothesis fell apart. No civilization would scatter identical beacons all over the galaxy. Something natural was producing these astonishingly precise pulses. The answer turned out to be rapidly rotating neutron stars with strong magnetic fields. The objects Jocelyn Bell Burnell had discovered were pulsars, and the discovery opened an entirely new chapter in astrophysics. It remains one of the most important astronomical discoveries of the 20th century. Here's how a rotation-powered pulsar works. A neutron star spins. It also possesses an intense magnetic field. And in most neutron stars, the magnetic axis, the imaginary line connecting the north and south magnetic poles, is not aligned with the rotation axis, the line the star spins around. The two axes are tilted relative to each other, sometimes by a large angle. This misalignment is the key to everything. Near the magnetic poles, the intense magnetic field creates conditions where charged particles, electrons, and their antimatter counterparts called positrons are accelerated to nearly the speed of light. As these particles stream outward along magnetic field lines, they produce concentrated beams of electromagnetic radiation, mostly radio waves, but sometimes also visible light, X-rays, and gamma rays. These beams emerge from the regions near the magnetic poles and shoot outward into space like twin searchlights. Because the magnetic axis is tilted relative to the rotation axis, as the neutron star spins, those beams sweep around in circles, tracing cones across the sky. If Earth happens to lie along the path that one of those beams traces, we see a flash of radiation every time the beam sweeps past us, one flash per rotation. The star itself has not switched on and off. It is radiating continuously from its magnetic poles. But from our perspective, we see a pulse each time the beam crosses our line of sight, and darkness the rest of the time. The principle is identical to a lighthouse. The light inside the lighthouse is always on. It never blinks. But because the lantern rotates, anyone watching from shore sees a periodic flash. Pulsars work the same way. They are not blinking. They are spinning. Their surfaces do not flash on and off. Their beams are always there, always streaming from the magnetic poles. We see pulsars only because of geometry, because those beams happen to sweep past our particular vantage point in space. This geometric requirement has a major consequence. If a neutron star's beams never cross our line of sight, we never detect it as a pulsar, even though it is still there, still spinning, still producing beams aimed somewhere else in the cosmos. The neutron star is fully active, but from our perspective, it might as well be one of the quiet, cooling objects we just discussed. Estimates suggest that for every pulsar we detect, there are likely several more whose beams miss Earth entirely. The beams are relatively narrow. We probably observe somewhere between roughly 10 and 30% of all active rotation-powered pulsars in our galaxy. The rest are sending their signals into regions of space where nobody happens to be watching. The energy that drives a pulsar's emission comes directly from the star's rotation. This is what gives the category its full name: rotation-powered pulsar. The rapidly spinning magnetic field acts like a colossal dynamo, converting the kinetic energy stored in the star's spin into electromagnetic radiation and high-speed streams of energetic particles. This conversion process is remarkably powerful. A young, fast-spinning pulsar can pour out energy equivalent to the output of tens of thousands of ordinary stars, all of it drawn from the vast reservoir of rotational energy the neutron star carries. But this process comes at a cost. Every joule of energy the pulsar radiates into space is a joule subtracted from its rotation. The pulsar is gradually slowing down. This spin down is not dramatic on human timescales. A typical pulsar might lose a tiny fraction of a billionth of a second from its rotation period each day. You would never notice it from one pulse to the next, but over millions and tens of millions of years, the slowdown accumulates. A pulsar born spinning 30 times per second might, after a few million years, rotate only a handful of times per second. After tens of millions of years, it might spin only once every few seconds. And eventually, it reaches a critical threshold. Astronomers call this threshold the death line. It is the boundary below which a pulsar can no longer sustain its emission mechanism. When a neutron star's spin has slowed too much, the electric fields generated by its rotating magnetosphere become too weak to tear charged particles from the surface, or produce the cascading showers of electrons and positrons that create the radio beams. The beams fade. The pulsar effectively switches off. It stops producing detectable radiation of this kind and becomes, once again, a quiet neutron star coasting through the galaxy in silence. This spin-down process explains something important about the population of known pulsars. Most detected pulsars have rotation periods between roughly 1/10 of a second and a few seconds. Very few have periods shorter than about 20 milliseconds, because those extremely fast pulsars belong to a special category with a very different origin story that we will come to later. And very few have periods longer than about 8 or 10 seconds, because pulsars that have slowed that much have typically already crossed the death line or become so faint that detecting them is extraordinarily difficult. Astronomers have a powerful tool for visualizing all of this. If you create a chart with spin period on one axis and the rate at which the spin is slowing on the other axis, every known pulsar appears as a point on that chart. A striking pattern emerges. Young, energetic pulsars cluster in one region, spinning fast and slowing down rapidly. As they age, they migrate across the chart towards slower spin and less rapid slowdown. Eventually, they cross the death line and vanish from the detectable population entirely. This single diagram captures the complete life arc of a rotation-powered pulsar, from birth to silence, in one image. Some of the most celebrated neutron stars in astronomy are young pulsars caught early in this journey, blazing with energy and surrounded by the debris of their own creation. The Crab pulsar is perhaps the most famous example. It sits at the heart of the Crab Nebula, a cloud of expanding gas and dust that has captivated astronomers for centuries. The Crab Nebula is the remnant of a supernova that was observed on Earth in the year 1054. Chinese astronomers recorded a brilliant guest star appearing in the sky that year, so bright it was visible during daylight for several weeks. Japanese and Arab observers likely noted it as well. What those ancient sky watchers were witnessing was a massive star tearing itself apart in a supernova explosion. And at the center of that explosion, a neutron star was born. The Crab pulsar spins roughly 30 times per second. It's only about 1,000 years old, which in neutron star terms is extremely young, practically a newborn. It radiates across the entire electromagnetic spectrum, from radio waves through visible light all the way up to gamma rays, and it is one of the most energetic pulsars known. The torrent of energy pouring out of the Crab pulsar is what keeps the entire Crab Nebula glowing nearly 1,000 years after the explosion that created both of them. Without the pulsar at its center, continuously injecting energy into the surrounding gas through a fierce wind of particles moving at close to the speed of light, the nebula would have faded long ago. The Crab Nebula is essentially a pulsar-powered lantern that has been shining since the Middle Ages. The Vela pulsar is another well-studied young example. At roughly 11,000 years old, it is older than the Crab pulsar and spins more slowly, about 11 times per second, reflecting the extra millennia of spin down it has experienced. It sits inside its own supernova remnant. a shell of expanding gas that marks the site of the explosion. Vela is one of the brightest gamma-ray sources in the sky, and has taught astronomers an enormous amount about pulsar physics. One of the most fascinating things the Vela pulsar does is glitch. Every now and then, its spin rate suddenly increases by a tiny amount, then gradually settles back toward its previous value. These glitches are not malfunctions. They are windows into the physics of the neutron star's hidden interior. The leading explanation is that deep inside the neutron star, a superfluid, a friction-free quantum liquid made of neutrons, rotates slightly faster than the solid outer crust. Normally the superfluid and the crust are loosely coupled, spinning at slightly different rates, but occasionally angular momentum is suddenly transferred from the faster spinning interior to the crust, causing the crust to speed up in a tiny but measurable jump. These glitches provide some of the best evidence we have for the exotic states of matter that exist inside neutron stars, in regions so deep and so dense that no laboratory on Earth could ever recreate them. These young, energetic pulsars are the celebrities of the neutron star world. They are bright, detectable across enormous distances, and they power spectacular nebulae that look stunning in telescope images. But they are rare. Most detected pulsars are considerably older, considerably dimmer, and far less dramatic. They spin more slowly, radiate less energy, and are quietly creeping toward the death line. The typical pulsar an astronomer discovers is probably somewhere between a few 100,000 and a few million years old, spinning roughly once per second, gradually fading towards silence. And when a pulsar does finally cross the death line, when its rotation can no longer sustain beams of radiation, what remains? A neutron star, still unimaginably dense, still massive, still carrying a magnetic field, though that field may have weakened somewhat over millions of years as electric currents in the crust slowly dissipate, but no longer visible as a pulsar. The object quietly joins the vast, invisible population of ordinary cooling neutron stars. It has not changed in any fundamental way. It is the same object it was when it was a young, energetic beacon. It has simply run out of the spin energy needed to make itself seen. This is the first and perhaps the most important lesson about neutron star classification. A pulsar is not a different thing from a neutron star. It is a neutron star caught in a particular phase of its life, when its spin rate and magnetic field combine to produce detectable beams of radiation that happen to sweep past Earth. The word pulsar describes a behavior and a circumstance, not a permanent identity. When the behavior stops, the neutron star does not vanish from existence. It simply fades from our view. And this principle extends far beyond pulsars. It applies to nearly every other category of neutron star we are about to encounter. The names astronomers use, pulsar, magnetar, millisecond pulsar, accreting X-ray source, central compact object, are not labels for different species. They are labels for different states, different physical conditions, different snapshots of the same kind of object under different circumstances. A neutron star can transition from one state to another. It can occupy more than one category at the same time. The labels overlap and intersect in ways researchers are still working to untangle. Think about the journey we have traced so far. A massive star dies. Its core collapses. A neutron star is born carrying a particular mass, spin rate, temperature, and magnetic field strength. If the spin and magnetic field produce the right conditions and the geometry is favorable, we see a pulsar. Over millions of years, the pulsar spins down. It crosses the death line. It fades into the silent majority of cooling neutron stars. That is the default trajectory, the simplest possible life story for a neutron star. But nature rarely sticks to the simplest story. Some neutron stars are born with magnetic fields so extraordinarily powerful that they behave in ways completely unlike ordinary pulsars. Some find themselves in binary star systems where a companion fundamentally alters their evolution. Some are spun back up to dizzying speeds long after they should have faded into silence. And some are forged not in supernovae, but in mergers, collisions between two neutron stars that create brief, violent remnants lasting only fractions of a second before collapsing into black holes. The quiet, cooling neutron star is the canvas. The rotation-powered radio pulsar is the first figure painted on that canvas. The most familiar illustration of how spin and magnetism can turn a dense, silent ball of neutrons into something visible across the galaxy. But there are many more figures to come. Some are driven by magnetism more extreme than anything else in the known universe. Some are powered by matter stolen from a companion star. Some sit at the boundaries between categories, defying easy classification and challenging astronomers to rethink what they thought they understood. The diversity of neutron stars is not a confusing accident. It is a natural and elegant consequence of extreme physics. When you take an object that exists at the very edge of what matter can do, an object with the strongest surface gravity of any solid body in the cosmos, magnetic fields trillions of times more powerful than Earth's, and spin rates that would tear any ordinary object to pieces, and then you allow those properties to vary even slightly from one neutron star to the next, you get dramatically different observable behaviors. A modest difference in magnetic field strength can mean the difference between a steady pulsar and a violent erupting magnetar. A small difference in spin period can mean the difference between visibility and invisibility. A nearby companion star can completely reshape a neutron star's entire evolutionary path over the course of millions of years. This extreme sensitivity to initial and evolving conditions is exactly what makes neutron stars one of the most powerful natural laboratories in all of science. Each type lets us study a different regime of extreme physics. And the connections between the types, the pathways a neutron star can follow as it evolves from one category into another, reveal how those extreme conditions change across vast stretches of cosmic time. The story of neutron star types is not merely a catalogue of curiosities. It is a window into some of the most extraordinary physics the universe has to offer, and we are only just getting started. We left off with the most familiar type of neutron star, the rotation-powered radio pulsar, an object that converts the energy stored in its own spin into beams of radiation sweeping across the cosmos. But we also hinted that rotation is not the only engine a neutron star can run on. Some neutron stars are born with magnetic fields so overwhelmingly powerful that the field itself becomes the dominant source of energy, producing behavior so violent and so unpredictable that it makes even the most energetic pulsar look tame by comparison. These are magnetars, and they represent one of the most extreme physical environments found anywhere in the known universe. Every neutron star has a strong magnetic field. That is one of the shared traits we established earlier. A typical neutron star might carry a magnetic field roughly 1 trillion times stronger than Earth's. That is already staggering. A refrigerator magnet has a field of roughly 100 Gauss. Earth's magnetic field at the surface is about half a Gauss. A typical neutron star's field is on the order of 1 trillion Gauss. At that strength, a magnetic field would erase the magnetic stripe on every credit card on Earth from halfway across the solar system. But magnetars operate on an entirely different level. A magnetar's magnetic field is roughly 100 to 1,000 times stronger than a typical neutron star's field. We are talking about fields on the order of 100 trillion to a quadrillion Gauss. These are the strongest magnetic fields known to exist anywhere in the universe. Nothing else comes close. Not the magnets in particle accelerators, not the fields around the stars, not the fields at the centers of galaxies. Magnetars hold the record, and they hold it by an enormous margin. At these field strengths, physics becomes genuinely exotic. The magnetic field is so intense that it distorts the very structure of atoms. In a field this strong, atoms are squeezed into elongated, needle-like shapes, stretched along the field lines. The vacuum of empty space itself becomes birefringent, meaning it bends light differently depending on its polarization. A prediction of quantum electrodynamics that has been partially confirmed through observations of magnetar emission. The field contains an astonishing amount of energy. In fact, the energy stored in a magnetar's magnetic field can exceed the total energy output of our sun over tens of thousands of years. And it is this stored magnetic energy that powers a magnetar's extraordinary behavior. Unlike a rotation-powered pulsar, which draws its energy from spin, a magnetar is powered primarily by the decay and reorganization of its magnetic field. As the field evolves over time, its structure changes. Field lines can become tangled, twisted, and stressed, storing energy like a coiled spring being wound tighter and tighter. Eventually that stress is released, and the release can be spectacularly violent. The most common form of magnetar activity is the emission of short, intense bursts of X-rays and gamma rays. These bursts can last anywhere from a fraction of a second to a few seconds, and during that brief window, the magnetar can release as much energy as our sun produces in an entire year. These are not gentle emissions. They are explosions of radiation triggered by sudden rearrangements of the magnetic field, often accompanied by fractures in the neutron star's crust. That last detail deserves some unpacking. A neutron star has a solid outer crust. It's not a liquid ball. The outermost layer, perhaps a mile or so thick, is composed of a crystalline lattice of atomic nuclei embedded in a sea of electrons, forming an extraordinarily rigid material. This crust is the strongest solid known to exist, vastly harder than any material on Earth. Steel, diamond, nothing on Earth comes close to the sheer rigidity of a neutron star's outer crust, though nuclear pasta layers near the base of the inner crust may be even stronger still. But even this incredibly strong material has a breaking point, and a magnetar's magnetic field can exceed that breaking point. When the evolving magnetic field places too much stress on the crust fractures. This fracture is what astronomers call a starquake. It is not like an earthquake in the usual sense. An earthquake on our planet involves tectonic plates shifting, releasing energy accumulated over years or decades. A starquake on a magnetar involves the sudden cracking of a crystalline shell under magnetic forces that dwarf anything geology has to offer. The energy released in a magnetar starquake can be millions of times greater than the most powerful earthquake ever recorded on Earth, and the rupture happens in milliseconds. When the crust fractures, the magnetic field snaps into a new configuration, and the released energy floods outward as a burst of high-energy radiation. Sometimes it also triggers a rearrangement of the magnetosphere, the region of space around the neutron star dominated by its magnetic field, sending a blast of energetic particles streaming outward. Most magnetar bursts are relatively modest on cosmic scales. They are intense, yes, far brighter than ordinary pulsar emission, but they are brief, and their energy output, while enormous by human standards, is not galaxy-shaking. However, on rare occasions, a magnetar produces something far more dramatic: a giant flare. A giant flare is the most energetic event a magnetar can produce. Only a handful have been observed in the history of modern astronomy, and the most powerful one ever recorded happened on December 27th, 2004. A magnetar designated SGR 1806-20, located roughly 50,000 light-years from Earth on the far side of our galaxy, erupted with a blast of energy so intense that it briefly outshone every other source in the Milky Way at gamma-ray wavelengths. In approximately 0.2 of a second, this single neutron star released more energy than our Sun produces in roughly 250,000 years. The burst was so powerful that it measurably disturbed Earth's ionosphere, the electrically charged upper layer of our atmosphere, from a distance of 50,000 light-years. It saturated the detectors on every gamma-ray satellite in orbit. Some instruments designed to measure the faintest signals from deep space were temporarily blinded. If this magnetar had been located much closer to Earth, say within 10 light-years, the consequences could have been catastrophic. The radiation could have stripped away a significant portion of our ozone layer, exposing the surface to lethal levels of ultraviolet radiation. Fortunately, magnetars are rare objects, and the odds of one being that close to us are extremely small. But the December 2004 event served as a vivid demonstration that the universe can produce bursts of energy from single objects that are almost incomprehensible in their ferocity. Giant flares of this magnitude are rare even for magnetars. Most magnetars go through long periods of relative calm, punctuated by occasional burst but nothing approaching the violence of a giant flare. Some magnetars are observed primarily in a quiescent state, producing steady but faint X-ray emission powered by residual heat and low-level magnetic field decay. They are not always erupting. The popular image of a magnetar as a perpetually exploding cosmic bomb is misleading. A magnetar is more accurately described as a neutron star with an enormous reservoir of magnetic energy that is slowly leaking away, occasionally releasing that energy in sudden, dramatic events, but spending most of its time in a comparatively quiet state. Historically, magnetars were discovered under two different labels. Some were initially classified as soft gamma repeaters, neutron stars that produced repeated bursts of gamma rays. Others were classified as anomalous X-ray pulsars, neutron stars that showed regular pulsations in X-rays, but whose energy output was too high to be explained by rotation alone. For years, these two categories were treated as separate phenomena. It was only later that astronomers realized both were manifestations of the same underlying physics: neutron stars with ultra-strong magnetic fields. The term magnetar unified both categories under a single physical explanation, showing that the bursting soft gamma repeaters and the steadily pulsating anomalous X-ray pulsars were the same kind of objects seen in different states of activity. This unification is a perfect example of how neutron star classification evolves. What begins as two separate categories, defined by how objects happen to look when we observe them, turns out to be one category, defined by the underlying physics that drives the behavior. The labels change as the understanding deepens. Magnetar activity does not last forever. The magnetic field that powers a magnetar's behavior is gradually decaying. Over thousands to tens of thousands of years, the field weakens, the stresses on the crust diminish, the bursts become less frequent and less energetic, and eventually the magnetar settles into a quieter existence. The neutron star does not disappear. It is still there, still unimaginably dense, still spinning. But it is no longer a magnetar in the active sense. Its extreme magnetic youth has passed. It may continue to emit as a rotation-powered pulsar if its spin and residual field allow it. Or it may fade into the silent population of cooling neutron stars we discussed earlier. The label magnetar describes a phase, not a permanent identity. And this brings us to a category that sits uncomfortably in the overlap between pulsars and magnetars. High magnetic field radio pulsars. These are neutron stars with magnetic fields that are unusually strong for pulsars, approaching or even reaching the range typically associated with magnetars, and yet they produce regular radio pulses like ordinary rotation-powered pulsars. Their existence blurs what might otherwise seem like a clean boundary between the two categories. Some of these objects have made the blurring even more dramatic by switching behavior. There are cases of neutron stars that were classified as ordinary young pulsars for years, producing steady radio and X-ray emission consistent with rotation-powered models, and then suddenly, without warning, produced magnetar-like bursts. These events stunned the astronomical community because they showed that a pulsar could, under the right internal conditions, briefly behave like a magnetar. The magnetic field was strong enough all along. Something about the internal dynamics simply had not triggered magnetar behavior until that moment. The lesson here is crucial. Magnetic field strength alone does not always determine how a neutron star behaves. Two neutron stars could have nearly identical surface magnetic field strengths, and one might act like a pulsar while the other acts like a magnetar. The difference might lie in the geometry of the field, whether it is primarily a simple two-pole configuration or a more complex, twisted structure that stores extra energy. It might lie in the age of the neutron star, since younger objects have had less time for their fields to relax. It might lie in the properties of the interior, where exotic states of matter could influence how magnetic stresses build and release. The boundary between pulsar and magnetar is not a sharp line drawn at a specific field strength. It is a gradient, a fuzzy zone where the two categories shade into one another. Now, let us turn to a category that adds yet another layer of ambiguity to the classification landscape: rotating radio transients. Rotating radio transients were discovered in 2006, and they presented astronomers with an immediate puzzle. These objects emit brief, sporadic bursts of radio waves. Unlike a regular pulsar, which produces a steady, predictable stream of pulses that you can set a clock by, a rotating radio transient might flash once, then remain silent for minutes, hours, or even longer before flashing again. Some produce a few pulses per hour. Some go quiet for extended stretches, and then briefly resume. The pattern is erratic and unpredictable. When astronomers analysed the timing of the bursts that were detected, they found an underlying periodicity. The bursts when they did occur, were spaced at intervals that were exact multiples of a base period, suggesting that the object was still rotating at a steady rate, just like a pulsar. But instead of producing a detectable pulse with every rotation, it was only producing an observable burst on a small fraction of its rotations. It was as if a lighthouse had a faulty bulb that only flickered on occasionally rather than shining with every sweep. What causes this intermittent behavior is not completely settled. Several explanations have been proposed. Some rotating radio transients may be ordinary pulsars whose emission mechanism operates near a threshold, switching on and off unpredictably as conditions in the magnetosphere fluctuate. In this picture, the pulsar is always there, always spinning, but its ability to produce a detectable radio beam comes and goes, perhaps because the supply of charged particles fueling the beam is unstable. Others may have a connection to magnetar activity. Some rotating radio transients have magnetic fields estimated to be in the range where magnetar behavior becomes possible, and a few have shown signs of X-ray emission that would be consistent with magnetic field decay, contributing to their energy output. It is possible that some of these objects represent a transitional state between active magnetars and ordinary pulsars, neutron stars whose magnetic activity is winding down but has not yet fully ceased. Still others might simply be distant, faint pulsars whose steady pulse trains are too weak to detect consistently. Individual bright pulses might occasionally rise above the noise floor of our telescopes, giving the appearance of sporadic behavior even though the underlying emission is continuous. The honest answer is that rotating radio transients are probably not one single physical phenomenon. The category likely includes multiple types of objects lumped together because they share a common observational signature: sporadic radio bursts from a rotating neutron star. As our telescopes improve and we accumulate more data, some of these objects will probably be reclassified into more specific categories. For now, they occupy a fascinating and somewhat unsettled corner of the neutron star zoo. From the most magnetically violent objects in the cosmos, let us now turn to some of the quietest. Because not all unusual neutron stars announce themselves with dramatic bursts or sweeping beams. Some are remarkable precisely because they are so subdued. Central compact objects are young neutron stars found near the geometric centers of supernova remnants, exactly where you would expect to find the leftover core of the star that exploded. They glow in X-rays, and their X-ray emission appears to be thermal, meaning it comes from the hot surface of the neutron star, rather than from any pulsar mechanism or magnetic eruption. They are simply hot and radiating that heat. So far, this sounds straightforward. A young neutron star is hot because it was just born in a supernova. It radiates X-rays from its surface, nothing unexpected there. But central compact objects have a peculiar trait that sets them apart from most young neutron stars. Their external magnetic fields appear to be remarkably weak, far weaker than what you would expect for a freshly minted neutron star. While a typical young pulsar might have a magnetic field of 1 trillion Gauss or more, the fields inferred for central compact objects can be hundreds or thousands of times weaker. This is surprising because neutron stars are expected to be born with strong magnetic fields, amplified from the original star's field during the violent compression of core collapse. So where did the magnetic field go? One possibility is that the magnetic field is not actually weak. It might be buried. During or shortly after the supernova, material can fall back onto the neutron star's surface. This fallback material could push the magnetic field lines down beneath the crust, effectively hiding them. In this scenario, the neutron star has a strong magnetic field, but it is trapped below the surface, invisible to our instruments. Over time, the field might slowly diffuse back up through the crust, eventually re-emerging and making the neutron star look more like a typical pulsar or even a magnetar. Another possibility is that some neutron stars genuinely are born with weak magnetic fields. Perhaps the dynamo process that amplifies the field during core collapse does not always operate at full efficiency. Maybe some collapses produce cores that rotate too slowly or lack the right internal conditions to generate the intense fields seen in pulsars and magnetars. Only about 10 central compact objects have been identified, in part because detecting them requires finding a young supernova remnant with a neutron star at its center that is not producing strong radio pulses or magnetar-like bursts. They are quiet objects in a noisy field of study, easy to overlook. The best studied example sits at the center of the Cassiopeia A supernova remnant, one of the youngest known supernova remnants in the Milky Way. The explosion that created it occurred roughly 340 years ago as seen from Earth, making its central compact object an extremely young neutron star, practically a newborn by cosmic standards. Observations of this object have actually allowed astronomers to measure how quickly a neutron star cools in its first few centuries of life, providing direct constraints on the exotic physics operating deep inside these objects. That cooling measurement deserves closer attention because it illustrates just how much a quiet, unassuming neutron star can teach us. In 2010, a team of astronomers compared a decade's worth of X-ray observations of the Cassiopeia, a central compact object, and found that the neutron star's surface temperature had dropped measurably over just 10 years. That might not sound dramatic, but for a neutron star, it was extraordinary. Neutron stars are expected to cool, yes, but the rate at which they cool depends entirely on what is happening in their interiors, in regions so dense that the physics governing them is uncertain. Different theoretical models of neutron star matter predict different cooling rates. Some predict slow, steady cooling. Others predict that at a certain point in the star's life, exotic processes kick in and the cooling accelerates sharply. The Cassiopeia A observation appeared to catch a neutron star at exactly that transition point. The rate of temperature decline was consistent with a process called Cooper pair neutrino emission, in which neutrons in the star's core begin forming a superfluid state, and the transition into superfluidity releases a burst of neutrinos that carry heat away from the interior much faster than normal processes would allow. If confirmed, this would be direct observational evidence for neutron superfluidity, a quantum mechanical state of matter occurring on a scale of 12 miles rather than in a laboratory flask. Not all researchers agree on the interpretation. Some have argued that the apparent temperature decline could be an artifact of changing conditions in the neutron star's thin atmosphere, rather than a true interior cooling signature. The debate continues. But the fact that a central compact object, one of the quietest and least dramatic categories of neutron star, could provide evidence bearing on one of the deepest questions in nuclear physics, illustrates a point worth remembering. In neutron star science, the quiet objects are not necessarily the least interesting. Sometimes they are the most revealing precisely because their simplicity strips away complications and lets the fundamental physics shine through. The buried magnetic field hypothesis also has testable consequences that astronomers are actively pursuing. If a central compact object's magnetic field truly is trapped beneath the crust by fallback material, then as the field slowly diffuses back toward the surface over thousands of years, the neutron star's observable properties should change. It might begin to show faint radio pulsations as the re-emerging field starts to generate the conditions needed for a pulsar mechanism. It might even eventually display magnetar-like activity if the re-emerging field is strong and complex enough to stress the crust. In this picture, a central compact object is not a permanently quiet object. It is a temporarily quiet one, a neutron star whose magnetic youth has been delayed rather than absent. Now, contrast central compact objects with another category of quiet neutron star that appears very different at first glance but shares the trait of subdued behavior. X-ray dim isolated neutron stars. These are neutron stars that were discovered through their soft, thermal X-ray emission, much like central compact objects. They lack strong radio pulsations. They do not show magnetar-like bursts. They are detected primarily because they are close enough to Earth for their faint thermal glow to register on sensitive X-ray telescopes. The first handful of these objects were discovered by the ROH-SAT X-ray satellite in the 1990s, and the initial group of 7 became informally known as the Magnificent Seven, a name that has stuck in the astronomical community. At first glance, X-ray dim isolated neutron stars might seem similar to central compact objects. Both are quiet. Both emit thermal X-rays. Both lack strong radio pulsations. But they represent fundamentally different populations at different stages of their lives. And understanding the distinction is important for seeing how neutron stars evolve. Central compact objects are young. They are found inside supernova remnants that are at most a few tens of thousands of years old and often much younger. They have surprisingly weak external magnetic fields. They are hot because they were recently born. X-ray dim isolated neutron stars, by contrast, are considerably older. Their ages are estimated at several 100,000 years to perhaps 1,000,000 years. They are not found inside recognizable supernova remnants because any remnant from their birth explosion has long since dissipated into the surrounding interstellar medium. Their magnetic fields are moderate, stronger than those of central compact objects, but generally weaker than those of active magnetars. And their thermal X-ray emission comes not from the intense heat of recent birth, but from the residual warmth left over after hundreds of thousands of years of gradual cooling. The reason X-ray dim isolated neutron stars are detectable at all is proximity. They happen to be located within roughly 1,000 light years of Earth, close enough for their faint thermal glow to be picked up by orbiting X-ray observatories. If these same objects were located on the far side of the galaxy, they would be completely undetectable. This raises an important question. How many similar objects are out there, too distant for us to see? The answer is almost certainly a very large number. The Magnificent Seven are probably just the closest representatives of a vast population of quietly cooling neutron stars scattered throughout the galaxy. Objects that were once active pulsars or perhaps even magnetars, but have since faded into thermal obscurity. The spin periods of X-ray dim isolated neutron stars are also telling. They tend to rotate relatively slowly, with periods of several seconds. This is consistent with objects that were once faster spinning pulsars that have spun down over hundreds of thousands of years, crossing the death line and losing their ability to produce radio beams. their moderate magnetic fields would have driven this spin down over time, extracting rotational energy and converting it into radiation until the spin became too slow to sustain the pulsar mechanism. There is another important clue hidden in the spatial motions of X-ray dim isolated neutron stars. Several of them are moving through space at relatively high velocities, hundreds of kilometers per second in some cases. These speeds are consistent with the natal kicks that neutron stars receive during their supernova births. The violent, asymmetric nature of a core collapse explosion can launch the newborn neutron star in a random direction at considerable speed. Over hundreds of thousands of years, that kick carries the neutron star far from its birthplace, which is why X-ray dim isolated neutron stars are found drifting through the general interstellar medium rather than sitting inside identifiable supernova remnants. The remnants from their births dissipated long ago, and the neutron stars themselves have traveled considerable distances since then. By tracing these motions backward in time, astronomers have attempted to connect individual X-ray dim isolated neutron stars to specific regions of past star formation, trying to reconstruct where and when each one was born. This kind of detective work is difficult because the uncertainties compound over hundreds of thousands of years of travel. But in a few cases, plausible associations have been identified, linking a quietly cooling neutron star observed today to a specific stellar nursery where its progenitor star likely formed and died. The fact the all-known X-ray dim isolated neutron stars are within roughly 1,000 light-years of Earth also raises a statistical question that bears on the total neutron star population. If we can detect 7 of them within this small local volume, how many similar objects must exist across the entire galaxy? The answer, based on straightforward extrapolation, is enormous. There could be hundreds of thousands or even millions of similar quietly cooling neutron stars scattered throughout the Milky Way, far too distant for their faint thermal glow to register on even our most sensitive instruments. These invisible objects vastly outnumber the active pulsars and magnetars that dominate the headlines. They are the true silent majority of the neutron star population, and the X-ray dim isolated neutron stars we can actually detect are merely the closest handful of representatives from this immense hidden population. So here is how the pieces fit together. A neutron star is born in a supernova. If it is very young and has an unusually weak external magnetic field, perhaps because that field is buried beneath fallback material, it might appear as a central compact object, sitting quietly at the heart of a fresh supernova remnant and glowing in thermal X-rays. If the field eventually re-emerges, the neutron star might transition into a more conventional pulsar, or possibly even show magnetar-like behavior if the re-emerging field is strong enough. Alternatively, a neutron star born with a more typical magnetic field might spend its youth as an active rotation-powered pulsar, beaming radio waves across the galaxy for millions of years. As it spins down and crosses the death line, it fades from the pulsar population. If it happens to be nearby, we might still detect it as an X-ray dim isolated neutron star, quietly radiating the last of its thermal reserves. Or a neutron star born with an extraordinarily powerful magnetic field might blaze through a few thousand years of magnetar activity, producing bursts and flares and starquakes before the field decays enough to calm the fireworks. The residual field might still be strong enough to make it a high magnetic field radio pulsar for a while. Eventually that too fades, and the object joins the quiet cooling population. These are not separate species. They are different chapters in the life story of the same kind of object. The central compact object, the rotation-powered pulsar, the magnetar, the high magnetic field pulsar, the rotating radio transient, the X-ray dim isolated neutron star, all of these can be understood as different stages or different manifestations of a neutron star's evolution, shaped by the specific combination of spin, magnetic field strength, field geometry, age, temperature, and proximity to Earth. And there is one factor we have not yet fully explored, a factor that can completely rewrite a neutron star's life story and push it into categories that would be impossible for an isolated object to ever reach on its own. That factor is a companion. When a neutron star is not alone in space, but instead orbits close to another star, the interaction between them can transform the neutron star in ways that are dramatic, counterintuitive, and in some cases, almost paradoxical. A pulsar that should be dead and silent can be brought back to life. A neutron star that should be spinning lazily can be spun up to hundreds of rotations per second. A steady rotation-powered emitter can flicker back and forth between entirely different modes of behavior on timescales of weeks. Companions do not merely modify a neutron star's evolution. They can reverse it, restart it, and redirect it down entirely new paths. The isolated neutron stars we have encountered so far follow a broadly predictable arc. They are born, they spin down, they cool, they fade. Companions break that arc wide open. And the categories that emerge from binary interactions, millisecond pulsars, accreting X-ray sources, transitional systems, are some of the most fascinating and scientifically valuable objects in all of astrophysics. They reveal physics that no isolated neutron star could ever demonstrate on its own. And they prove beyond any doubt that neutron star classification is not about permanent identities. It is about circumstances that can change. But before we can understand how companions transform neutron stars, we need to understand how matter flows from one star to another, how that flowing matter carries angular momentum, and how the transfer of angular momentum can spin a neutron star up from near death to the fastest rotation rates observed anywhere in the cosmos. Because the process that creates a millisecond pulsar is one of the most elegant and counterintuitive recycling stories in all of nature. A dead pulsar, resurrected by its neighbor, given a second life that can outlast the galaxy itself. At the end of our last stretch of this journey, we arrived at a crucial turning point. We had traced the lives of isolated neutron stars, objects born alone in space, spinning down, cooling off, and eventually fading into silence. We explored how rotation powers pulsars, how extreme magnetism powers magnetars, and how quiet populations like central compact objects and X-ray dim isolated neutron stars represent different stages of a neutron star's solitary existence. All of these categories describe what a neutron star does when it is left to its own devices, evolving under the influence of its own spin, its own magnetic field, and the slow leak of its own internal heat. But not every neutron star is alone. And when a neutron star has a companion, everything changes. The majority of massive stars in the Milky Way are born in binary systems, orbiting a partner star. When one of these massive stars dies and leaves behind a neutron star, the binary system often survives the explosion. The supernova may disrupt the orbit, making it wider or more elliptical, or it may kick the neutron star to a high velocity. In some cases, the system is disrupted entirely, and the two stars fly apart. But in many cases, the neutron star remains gravitationally bound to its companion, orbiting it for millions or billions of years after the explosion. At first, this might not make much difference. The neutron star orbits its companion at a distance, spinning down and cooling like any isolated neutron star would. But companion stars evolve too. And when a companion star reaches a certain stage in its own life, when it begins to expand and swell as it ages, something remarkable can happen. The companion can grow large enough that its outer layers extend beyond a critical gravitational boundary, a teardrop-shaped surface called the Roche lobe. Beyond this boundary, the companion's own gravity is no longer strong enough to hold onto its material. Gas from the companion's outer atmosphere spills across the boundary and falls toward the neutron star. This is accretion, and it transforms a neutron star's life in ways that would be impossible for any isolated object. The gas does not fall straight onto the neutron star's surface. It carries angular momentum, the rotational energy of the companion star's outer layers. Because of this angular momentum, the gas spirals inward, forming a swirling disk of material around the neutron star, called an accretion disk. The disk is not a calm, placid structure. It is a violent, turbulent, superheated vortex. As gas spirals inward through the disk, friction between adjacent layers heats the material to extraordinary temperatures. By the time the gas reaches the inner edge of the disk, close to the neutron star's surface, it has been heated to millions of degrees. At these temperatures, the gas emits intense X-ray radiation, making the system visible as a bright X-ray source even from across the galaxy. But the accretion disk does not extend all the way down to the neutron star's surface, at least not in a simple, uniform way. The neutron star's magnetic field intervenes. At a certain distance from the star, the magnetic field becomes strong enough to disrupt the disk's flow and seize control of the infalling gas. From this point inward, the gas is no longer free to spiral however it pleases. Instead, it is channeled along the magnetic field lines, funneled down toward the neutron star's magnetic poles, like water flowing along invisible rails. The gas crashes onto the neutron star's surface at the magnetic poles, releasing an enormous amount of gravitational energy as it decelerates from near light speed to a dead stop. This impact creates localized hotspots at the magnetic poles, regions where temperatures can reach tens of millions of degrees. These hotspots blaze with X-ray emission far brighter than the surrounding surface. Now, if the magnetic poles are offset from the neutron star's rotation axis, which they usually are, something familiar happens. As the neutron star rotates, those blazing hotspots sweep in and out of our line of sight. We see a regular pulsation in the X-ray brightness. Not because the star is switching on and off, but because the bright regions are rotating with the star, just like the beams of a rotation-powered radio pulsar. This is an X-ray pulsar, and it is one of the most important categories of neutron star in modern astrophysics. But here is the crucial distinction, the one that trips up even people who know a fair amount about astronomy. A rotation-powered radio pulsar and an accretion-powered X-ray pulsar both produce pulsars. Both involve a spinning neutron star with a misaligned magnetic axis. Both show regular periodic variations in their brightness. The word pulsar appears in both names, and yet the two objects are powered by fundamentally different engines. A rotation-powered radio pulsar converts the kinetic energy stored in its own spin into beams of radiation. The energy comes from within the neutron star itself, from the vast reservoir of rotational energy it received at birth. Every photon the pulsar emits costs it a tiny fraction of its spin. The pulsar is spending its own inheritance, and when that inheritance runs out, when the spin has slowed too much, the emission stops. An accretion-powered X-ray pulsar, by contrast, is fueled by gravity. The energy comes from outside, from gas falling inward from the companion star. As that gas descends into the neutron star's gravitational well, it converts gravitational potential energy into thermal energy and radiation. The neutron star is not spending its own rotational reserves. It is fed by an external fuel source. As long as the companion keeps supplying gas, the X-ray pulsar keeps shining. Same word, same basic geometry, completely different physics. This is one of the reasons neutron star classification can be confusing. The terminology was developed historically, as different types of objects were discovered, and the names sometimes emphasize surface similarities rather than underlying mechanisms. But understanding the distinction between rotation-powered and accretion-powered pulsars is essential to understanding the full landscape of neutron star types. Accreting neutron stars appear in two broad categories of binary system, distinguished by the mass of the companion star. In a high-mass X-ray binary, the companion is a massive star, often 10 or more times the mass of our Sun. These systems tend to be young, because massive stars live fast and die young. The companion might be a hot blue giant or supergiant, and it can lose material either through a powerful stellar wind or by overflowing its Roche lobe. The neutron star in a high-mass X-ray binary typically has a strong magnetic field, because the system is young and the field has not had time to decay significantly. The strong field channels the accreting gas effectively, creating bright X-ray hotspots and producing strong, easily detected X-ray pulsations. Centaurus X3, one of the first X-ray pulsars ever discovered, is a textbook example of a high-mass X-ray binary. Its neutron star orbits a massive blue supergiant companion, accreting material from the companion's stellar wind, and pulsing in X-rays with a period of about 4.8 seconds. In a low-mass X-ray binary, the companion is a much less massive star, typically less than or comparable to the mass of our Sun. These systems can be very old, billions of years old in some cases, because low-mass stars live for a very long time. The companion overflows its Roche lobe and feeds gas to the neutron star through a well-developed accretion disk. Low-mass X-ray binaries are particularly important because of what they can do to the neutron star's spin. Remember, the gas flowing toward the neutron star carries angular momentum. When it crashes onto the surface, it does not just deliver energy, it delivers a push, a rotational nudge. Every bit of accreted material adds a tiny increment of angular momentum to the neutron star, spinning it up ever so slightly. One bit of gas makes no noticeable difference, but accretion can continue for millions or even billions of years. Over that immense span of time, the cumulative effect is transformative. A neutron star that had spun down to a sluggish rotation of perhaps once every few seconds can be accelerated back up to hundreds of rotations per second. An object that should be dead, that should have long ago crossed the pulsar death line and faded into silence, is brought back to life, spun up, recycled. This is the origin of millisecond pulsars, and it is one of the most elegant evolutionary stories in all of stellar physics. A millisecond pulsar is a neutron star that rotates extraordinarily fast, typically completing hundreds of rotations every second. The fastest known millisecond pulsar, located in a dense stellar cluster called Terzan 5, spins at roughly 716 times per second. Think about that for a moment. An object with more mass than our Sun, compressed into a sphere 12 miles across, completing 716 full rotations every single second. The surface at the equator is moving at a significant fraction of the speed of light, potentially exceeding 20%. If the neutron star were spinning even marginally faster, the centrifugal force of the equator would overcome gravity and the star would tear itself apart. No neutron star is born spinning this fast. The supernova that creates a neutron star can produce initial spin rates of a few tens of rotations per second at most. To reach hundreds of rotations per second requires an external push, and that push comes from accretion. The millisecond pulsar was once a normal neutron star, probably a young pulsar that spun down over millions of years until it crossed the death line and went silent. But it happened to have a companion star. When that companion evolved and began transferring mass, the accretion process spun the neutron star back up, gradually accelerating it over millions or billions of years until it reached the dizzying speeds we observe today. This is why millisecond pulsars are sometimes called recycled pulsars. They have been through the cycle twice, born spinning fast, slowed down by magnetic braking, revived by accretion, now spinning fast again. They are second-generation pulsars, given a new lease on life by their companions. Millisecond pulsars differ from ordinary young pulsars in several important ways beyond just spin rate. Their magnetic fields are typically much weaker, often 1,000 to 10,000 times weaker than those of young pulsars. The exact reason for this weakening is still debated. It may be that the accretion process itself buries or screens the magnetic field. It may be that the field simply decays naturally over the billions of years these systems have been alive. Or it may be a combination of both effects. Regardless of the cause, the weaker magnetic field means that millisecond pulsars lose their rotational energy much more slowly than young pulsars do. They spin down at a glacial pace. A typical millisecond pulsar might take billions of years to slow down appreciably, far longer than the current age of the universe. This extraordinary stability makes millisecond pulsars some of the most precise, natural clocks in existence. Their pulses arrive with a regularity that rivals the best atomic clocks on Earth. Astronomers can predict the arrival time of a millisecond pulsar's pulses to within microseconds over spans of years. This precision has turned millisecond pulsars into scientific instruments in their own right. One of the most ambitious uses of millisecond pulsars is in pulsar timing arrays. The idea is elegant. If you monitor a network of millisecond pulsars scattered across the sky, and you measure the arrival times of their pulses with extreme precision, you can detect disturbances in the fabric of space-time itself. Gravitational waves, ripples in space-time produced by massive objects like orbiting supermassive black holes, will stretch and compress the space between Earth and the pulsars as they pass through. This stretching and compressing changes the travel time of the pulsar signals by tiny but measurable amounts. By looking for correlated changes in pulse arrival times across many pulsars simultaneously, astronomers can detect gravitational waves that are far too low in frequency for ground-based detectors to sense. In 2023, several pulsar timing array collaborations around the world announced strong evidence for a background hum of gravitational waves permeating the cosmos, likely produced by pairs of supermassive black holes slowly spiraling toward each other at distant galaxies. This detection was made possible entirely by the extraordinary precision of millisecond pulsars. Without recycled pulsars, without the accretion process that creates them. This entire field of gravitational wave science would not exist. Many millisecond pulsars are found in globular clusters, the dense, spherical collections of hundreds of thousands of old stars that orbit the Milky Way. Globular clusters are ideal breeding grounds for millisecond pulsars because the stars are packed so closely together that gravitational interactions are common. Neutron stars in these crowded environments have many opportunities to capture companion stars and enter into the binary systems needed for recycling. Some globular clusters contain dozens of known millisecond pulsars, far more per unit volume than the galaxy at large. The companions of millisecond pulsars have often been dramatically altered by the recycling process. By the time the spin-up is complete, the companion star may have lost a substantial fraction of its original mass. In some systems, the companion has been whittled down to a tiny remnant, a white dwarf that is only a fraction of our sun's mass. In extreme cases, the pulsar's intense radiation and particle wind can ablate the remaining companion, slowly eroding it away. These cannibalistic systems have earned colourful nicknames. When the companion is being actively destroyed, the system is sometimes called a black widow pulsar, named after the spider that devours its mate. When the companion is partially ablated but survives as a larger remnant, it is sometimes called a redback pulsar. The names are vivid, and they capture the violent asymmetry of these systems. The neutron star has taken what it needed from its companion, and is now destroying what remains. Now, here is where the story takes a truly remarkable turn. For decades, the evolutionary connection between accreting X-ray binaries and millisecond pulsars was a theoretical prediction. The argument was compelling. We observe low-mass X-ray binaries where neutron stars are currently accreting. We observe millisecond pulsars that show signs of past accretion. The theory said these should be the same objects at different stages. A low-mass X-ray binary is a millisecond pulsar being built, and a millisecond pulsar is a low-mass X-ray binary that has finished building. But no one had caught a system in the act of switching between these two states. Then, in 2013, astronomers found exactly that. A neutron star in a binary system inside the globular cluster Messier 28 was observed to switch between two completely different modes of behavior. At some times, it looked like a low-mass X-ray binary. Gas from the companion was flowing onto the neutron star, forming an accretion disk, and the system was bright in X-rays. At other times, the accretion stopped. The disk disappeared, and the neutron star switched on as a rotation-powered millisecond radio pulsar, producing the characteristic steady radio pulses of a recycled pulsar. The same object, the same neutron star, switching back and forth between accretion-powered behavior and rotation-powered behavior on timescales of weeks. This was the discovery of transitional millisecond pulsars, and it was a landmark moment in neutron star science. The physics behind the transition is a tug-of-war between the infalling gas and the neutron star's rotating magnetic field. When accretion is strong, the ram pressure of the infalling gas overwhelms the magnetic field's ability to push material away. Gas penetrates to the neutron star's surface, accretion proceeds, and the system behaves as an X-ray binary. But when the accretion rate drops, the balance shifts. The neutron star's rapidly rotating magnetosphere acts like a propeller, flinging gas outward rather than letting it fall inward. With the accretion disk pushed back, the neutron star's rotation-powered emission mechanism switches on, and radio pulses emerge. The system can flicker back and forth between these states, as the accretion rate from the companion varies. It is like watching a light switch being toggled. One moment the neutron star is fed by its companion and shines in X-rays. The next moment the food supply dips below a critical threshold, the feeding stops, and the neutron star immediately reverts to broadcasting as a radio pulsar. The speed of these transitions stunned astronomers. Decades of gradual evolution between X-ray binary and millisecond pulsar states had been predicted by some models. A switch happening in a matter of days was not widely anticipated. Only a handful of confirmed transitional millisecond pulsars have been identified so far. They are rare, or at least rarely caught in the act, because the transitions are brief and unpredictable. You have to be watching the right object at the right time with the right instruments to catch the switch. But even a few confirmed examples have been enormously important because they prove something fundamental about how we should think about neutron star classification. The categories we have been discussing, rotation-powered pulsar, accreting X-ray source, millisecond pulsar, these are not permanent identities. A neutron star does not choose one label at birth and keep it forever. A transitional millisecond pulsar demonstrates this with dramatic clarity. The same physical object, the same neutron star with the same mass, the same radius, the same magnetic field, can be classified as two entirely different types, depending on whether gas happens to be falling onto it at that particular moment. The classification describes a state, not an essence. It describes what the neutron star is doing right now, not what it fundamentally is. This point cannot be overstated because it is the thread that ties this entire journey together. From the very beginning, we have been building toward this insight. An ordinary cooling neutron star is not a different creature from a pulsar. A magnetar is not a different species from a high magnetic field radio pulsar. An accreting X-ray source is not a fundamentally different object from a millisecond pulsar. They are all the same kind of thing. A ball of neutrons roughly 12 miles across, doing different things under different circumstances. Change the spin, and you change the category. Change the magnetic field, and you change the category. Add a companion, and you can rewrite the entire evolutionary trajectory. Remove the companion's fuel supply for a few weeks, and you change the category again. The labels are snapshots. The underlying object is continuous. Transitional millisecond pulsars are the clearest possible demonstration of this principle. They switch categories in real time while we watch, removing any remaining doubt that these classifications describe fluid, changing states rather than fixed, immutable types. And the story of neutron stars in binary systems does not end with millisecond pulsars and transitional systems. Because some binary systems contain not just one neutron star, but two. Some contain a neutron star and a white dwarf. Some may contain a neutron star and a black hole. These compact binary systems are among the most extreme gravitational laboratories in the universe. They set the stage for one of the most violent events in all of astrophysics, the merger of two neutron stars, an event that can briefly create an entirely new kind of neutron star. One that exists for only a fraction of a second before it either stabilizes or collapses into a black hole. The journey from isolated cooling object to recycled millisecond pulsar has shown us how a neutron star's environment can reshape its destiny. The journey from compact binary to merger remnant will show us something even more extraordinary. That a neutron star's story does not always end with a slow, quiet fade. Sometimes the final chapter is the most violent and the most revealing of all. creating conditions so extreme that they test the very limits of what matter itself can endure. But that is where our story goes next. Into the realm of binaries so tight that Einstein's general relativity becomes not just a theoretical framework, but a measurable, observable force. Into the collisions that generate gravitational waves detectable across the cosmos. And into the brief, blazing existence of merger remnants that push neutron star matter beyond anything we have encountered so far. Objects that may not even be neutron stars in the traditional sense. Objects that might contain forms of matter never seen anywhere else in the universe. We have now traced the life of a neutron star from the moment of its explosive birth through the quiet phase of cooling, through the lighthouse years of pulsar activity, through the violent eruptions of magnetar behavior, and through the transformative influence of a companion star that can spin a dead pulsar back to life as a millisecond pulsar. Along the way, we have seen how a single kind of object can wear many different faces, depending on spin, magnetism, age, temperature, and environment. But we have not yet reached the most extreme stage in the neutron star story. This stage is written not by aging or accretion, but by collision, by the merging of two compact objects in the most violent event the universe can produce, short of the Big Bang itself. To get there, we need to talk about compact binary systems. Systems where a neutron star orbits not a normal star, but another stellar remnant. A white dwarf, another neutron star, or possibly even a black hole. These systems are extraordinary gravitational laboratories, and some of them have provided the most precise test of Einstein's general theory of relativity ever conducted. The most common type of compact binary involving a neutron star is actually not a double neutron star system. It is a neutron star paired with a white dwarf. These systems form naturally as the end state of the recycling process we discussed earlier. A neutron star accretes matter from a companion star over millions or billions of years, spinning up to millisecond periods. When the companion exhausts its remaining fuel and can no longer sustain hydrogen fusion, it contracts and cools into a white dwarf. What remains is a millisecond pulsar orbiting a white dwarf companion. Two stellar remnants locked in a gravitational waltz that can last for billions of years. These systems are remarkably common. The majority of known millisecond pulsars are in binaries with white dwarf companions, and they are extraordinarily useful for precision physics. Because the millisecond pulsar is such a stable clock, astronomers can measure the orbital parameters with breathtaking accuracy. Tiny relativistic effects that would be invisible in any other context become measurable over years of patient observation. The Shapiro delay, a general relativistic effect where the pulsar signal takes slightly longer to reach Earth when it passes through the curved space-time near the white dwarf companion, has been measured in several of these systems. These measurements provide some of the most stringent tests of general relativity outside the strong field regime, and allow astronomers to determine the masses of both the neutron star and the white dwarf with remarkable precision. Neutron star white dwarf binaries also come in a dramatic variety. Some are tight systems where the orbital period is measured in hours. Others are wide systems where the orbital period stretches to weeks or months. The tight systems are particularly interesting because in some cases the white dwarf orbits so close to the neutron star that it is being irradiated and slowly ablated by the pulsar's energetic wind. The Black Widow and Redback systems we encountered earlier. the wide systems are valuable for different reasons. Their orbits are so clean, so free from the complicating effects of mass transfer and tidal interactions, that they serve as pristine laboratories for testing gravitational theories. Then there are the systems that pair a neutron star with a black hole. These are far rarer and far harder to confirm observationally. No electromagnetic observation has yet provided an unambiguous identification of a neutron star orbiting a black hole in a compact binary. But gravitational wave observations have begun to open this window. In 2020, the LIGO and Virgo detectors recorded a merger event in which one object had a mass consistent with a neutron star, and the other had a mass consistent with a black hole. A second probable neutron star black hole merger was detected around the same time. These detections were significant because they confirm that such systems exist and that they do eventually merge, producing gravitational waves detectable across cosmic distances. Neutron star black hole mergers are scientifically fascinating because their outcome depends on the mass ratio and the spin of the black hole. If the black hole is much more massive than the neutron star and is not spinning rapidly, it can swallow the neutron star whole, like a stone dropped into a pond, producing gravitational waves but little or no electromagnetic counterpart. The neutron star simply vanishes behind the event horizon before it can be disrupted. But if the mass ratio is more moderate or the black hole is spinning rapidly, tidal forces can tear the neutron star apart before it crosses the event horizon. In this case, some neutron-rich material is flung outward, potentially producing a kilonova and contributing to the cosmic budget of heavy elements, just as neutron star mergers do. The variety of compact binary systems involving neutron stars, neutron star white dwarf pairs that serve as precision physics laboratories, double neutron star systems that test general relativity and eventually merge in spectacular collisions, and neutron star black hole binaries that probe the boundary between the two densest objects in the universe, reflects the broader theme of this entire journey. The same fundamental object, a neutron star, appears in radically different contexts, depending on what it is paired with, and how that pairing evolves over time. Let us start with double neutron star systems. These are binaries in which both stars have already died, both have already exploded as supernovae, and both have left behind neutron star remnants that remain gravitationally bound to each other, orbiting their common center of mass. Forming such a system requires surviving 2 supernova explosions, which is not easy. The first supernova can disrupt the orbit or unbind the system entirely. The second supernova, when the companion also dies, is another chance for the system to fly apart. Only a fraction of massive binary stars successfully navigate both explosions and emerge as a double neutron star system. But the ones that do are scientific treasures. The most famous double neutron star system is the Hulse-Taylor binary pulsar, discovered in 1974 by Russell Hulse and Joseph Taylor. This system contains 2 neutron stars orbiting each other with a period of just under 8 hours. One of the neutron stars is an active radio pulsar, producing regular pulses that astronomers can time with exquisite precision. By tracking the arrival times of those pulses over years and decades, Hulse and Taylor were able to measure the orbital parameters of the system with extraordinary accuracy. What they found was remarkable. The orbit was shrinking. The 2 neutron stars were gradually spiraling closer together, their orbital period decreasing by a tiny but precisely measurable amount. The rate of this orbital decay matched, to within a fraction of a percent, the prediction made by Einstein's general relativity for energy loss through gravitational wave emission. The two neutron stars were radiating gravitational waves, ripples in the fabric of space-time itself, and those waves were carrying energy away from the system, causing the orbit to tighten. This was the first indirect detection of gravitational waves, decades before the direct detection would be achieved by ground-based observatories. Taylor received the Nobel Prize in Physics in 1993 for this discovery. Their binary pulsar proved that gravitational waves are real, that they carry energy, and that general relativity accurately describes gravity even in the most extreme environments. Almost 30 years later, an even more remarkable double neutron star system was discovered. Found in 2003, it is the only known binary in which both neutron stars are visible as active radio pulsars. This makes it an incomparably powerful laboratory. Having two pulsars means two independent clocks, two sets of pulse arrival times that can be compared against relativistic predictions simultaneously. Astronomers have used this system to measure multiple relativistic effects with extraordinary precision, including the Shapiro delay, gravitational redshift, and the rate of orbital precession. Every measurement agrees with Einstein's predictions. In fact, this system has confirmed general relativity to a precision of roughly 1 part in 10,000 in the strong field regime, surpassing even the Taylor binary. The system is also slowly spiraling inward due to gravitational wave emission, and it will merge in roughly 85 million years, far sooner than the Taylor system. When it does, it will produce the same kind of cataclysmic collision we are about to discuss. But for now, it remains the single most precise strong field test of gravity ever conducted. A pair of cosmic clocks falling toward each other while confirming the predictions of a theory written over a century ago. But the Taylor system did more than confirm Einstein's predictions. It also demonstrated something about the future of double neutron star systems. If the orbit is shrinking, if the two neutron stars are spiraling inward, then eventually they will collide. Not soon by human standards. The Taylor system will not merge for roughly 300 million years, but on cosmic timescales, that is a blink. And when they do merge, the result will be one of the most energetic events in the universe. Neutron star mergers are not hypothetical. We've observed one directly. On August 17th, 2017, the LIGO and Virgo gravitational wave detectors picked up a signal designated GW170817. The signal was unmistakable. It showed the characteristic chirp of two compact objects spiraling inward, orbiting each other faster and faster, the gravitational wave signal growing in frequency and amplitude until the two objects collided and the signal abruptly changed character. Analysis of the waveform showed that both objects had masses consistent with neutron stars, roughly 1.1 to 1.6 times the mass of our Sun each. This was the first direct detection of gravitational waves from a neutron star merger, but this event was extraordinary for another reason. Unlike the black hole mergers that LIGO had detected previously, a neutron star merger involves matter, actual physical stuff, and when that matter collides, it produces light. Within 2 seconds of the gravitational wave signal, a short burst of gamma rays was detected by orbiting telescopes. Within hours, astronomers around the world had pointed their telescopes at the source, a galaxy called NGC 4993, about 130 million light-years from Earth. And what they found there was a kilonova. A kilonova is the visible aftermath of a neutron star merger. During the collision, a fraction of the neutron-rich material is flung outward at a significant fraction of the speed of light. This ejected material is extraordinarily neutron-rich, and it immediately begins undergoing rapid nuclear reactions, building heavy elements through a process physicists call the R process, short for rapid neutron capture. In this process, atomic nuclei absorb neutrons faster than they can decay, building up heavier and heavier elements in a runaway chain. The R process is responsible for creating roughly half of all elements heavier than iron in the universe. Gold, platinum, uranium, thorium, many of the heaviest elements on the periodic table are forged not inside ordinary stars, but in the violent aftermath of neutron star mergers. The kilonova from the 2017 event was detected across the electromagnetic spectrum, from gamma rays through X-rays, ultraviolet, visible light, infrared, and radio waves. It faded over the course of days and weeks, its color shifting from blue to red as different radioactive elements decayed and contributed their energy to the glow. By analyzing the light from this kilonova, astronomers estimated that the merger produced many Earth masses worth of gold and platinum alone. A single neutron star collision created more precious metals in a fraction of a second than exists in our entire solar system. The 2017 detection was a watershed moment for astrophysics. It combined gravitational wave astronomy with traditional electromagnetic observations for the first time. It confirmed the theoretical prediction that neutron star mergers are a major source of heavy elements, and it raised a question that brings us to the final categories of neutron star in our journey. What happened to the merged object at the center of all that destruction? When two neutron stars collide, the resulting object is more massive than either of the original stars individually. The combined mass can exceed the maximum mass that a non-rotating neutron star can support. For a non-rotating neutron star, this maximum mass, called the Tolman-Oppenheimer-Volkoff limit, is believed to be somewhere around 2 to 2.3 times the mass of our Sun, though the exact value depends on the still uncertain properties of matter at extreme densities. If the merged object exceeds this limit, it cannot survive as a stable neutron star. It will collapse into a black hole. But collapse does not necessarily happen immediately. And this is where two final, extraordinary categories of neutron star enter the story: supramassive neutron stars and hypermassive neutron stars. Both are temporary objects, merger remnants that exist for only a brief window of time before their fate is sealed. But during that brief window, they represent conditions more extreme than anything else we have discussed. A supramassive neutron star is a merger remnant whose mass exceeds the Tolman-Oppenheimer-Volkoff limit for a non-rotating star, but is supported against collapse by rapid uniform rotation. The key word is uniform. The entire object rotates as a single, rigid body, spinning at nearly the maximum rate a neutron star can sustain without tearing itself apart. This rapid rotation provides additional centrifugal support, allowing the star to hold up more mass than it could if it was stationary. A supramassive remnant can potentially survive for seconds, minutes, or possibly much longer, depending on how quickly it loses angular momentum. As it radiates energy through gravitational waves, magnetic field interactions, and neutrino emission, it gradually spins down. and when its spin drops below the critical threshold needed to support its excess mass, it collapses into a black hole. A hypermassive neutron star is even more extreme. Its mass exceeds what even rapid uniform rotation can support. It survives only because of the differential rotation, meaning different layers of the star are spinning at different rates, and because of additional thermal pressure from the enormous heat generated by the collision. A hypermassive remnant is not a stable object by any definition. It is a brief, turbulent, superheated maelstrom of neutron-rich matter, spinning at different rates throughout its volume, held together by a precarious balance of forces that cannot last. Hypermassive remnants are believed to survive for at most a few tens of milliseconds to perhaps a few seconds before the differential rotation is smoothed out by internal viscosity and magnetic braking. The thermal pressure dissipates, and the object collapses into a black hole. In rare cases, the total mass of the merger might be low enough that the remnant falls below the Tolman-Oppenheimer-Volkoff limit, even for a non-rotating star. If that happens, the remnant does not need rotation to support itself. It can settle down as a stable, long-lived neutron star. This outcome is probably uncommon, since most neutron star mergers involve enough total mass to exceed the limit. But it is not impossible. A merger between two relatively low-mass neutron stars could, in principle, leave behind a stable remnant that would then cool and evolve like any other neutron star, perhaps eventually becoming a millisecond pulsar or simply a quiet cooling object. The exact fate of any particular merger remnant depends on factors that are still being actively researched. The total mass of the two original neutron stars matters enormously. The equation of state, the relationship between pressure and density inside neutron star matter, determines where the Tolman-Oppenheimer-Volkoff limit falls and how much additional mass rotation can support. Unfortunately, the equation of state at these extreme densities is one of the great unsolved problems in nuclear physics. We do not know the precise properties of matter squeezed to several times the density of an atomic nucleus. Different theoretical models give different predictions, and observations are still working to narrow down which models are correct. For the 2017 merger event, the fate of the central remnant is still debated. The gravitational wave signal alone could not definitively distinguish between a prompt collapse to a black hole and a brief hypermassive or supramassive remnant phase, followed by delayed collapse. The electromagnetic observations provided some clues, but not a definitive answer. Some analyses suggest that a short-lived remnant neutron star survived for a fraction of a second to a few seconds before collapsing. Others argue that the collapse was nearly instantaneous. This uncertainty itself is scientifically valuable because it constrains the equation of state. If the remnant survived even briefly, that tells us something about how stiff nuclear matter is at extreme densities. If it collapsed immediately, that tells us something different. Every merger observation tightens the constraints, bringing us closer to understanding matter under the most extreme conditions in the universe. This brings us to a related and deeply speculative question. What is a neutron star actually made of on the inside? Throughout this journey, we have called these objects neutron stars, and the name implies they are made of neutrons. In the outer layers, that is approximately correct. The crust is a crystalline lattice of nuclei and electrons. Below the crust, the density increases and matter transitions into a fluid of neutrons with a small admixture of protons and electrons. But at the very core, where densities can reach 5 to 10 times the density of a normal atomic nucleus. No one is entirely certain what happens. At these extreme densities, some theoretical models predict that neutrons themselves might break apart. Neutrons are not fundamental particles. They are made of quarks, specifically 3 quarks bound together by the strong nuclear force. Under sufficient pressure, the boundaries between individual neutrons might dissolve, and the quarks might roam freely in a state called quark matter. A neutron star with a core made of 3 quarks would be a hybrid star. Neutron matter on the outside, quark matter on the inside. If the entire star were composed of quark matter, it would be a quark star. There is an even more exotic possibility. A particular type of quark matter called strange quark matter, which contains roughly equal numbers of up quarks, down quarks, and strange quarks, has been hypothesized by some physicists to be the most stable form of matter in the universe. If this hypothesis is correct, then under sufficient pressure, ordinary nuclear matter would convert into strange quark matter, and the resulting object would be a strange star. A strange star would have different properties from a conventional neutron star. A different mass-radius relationship, a different cooling rate, potentially a different maximum mass. It is important to be clear about the status of these ideas. Quark stars, strange stars, and hybrid stars are theoretical proposals. They emerge from well-motivated physics, from our understanding of quantum chromodynamics, the theory of the strong nuclear force that governs quarks, and their interactions. But no observation has definitively confirmed the existence of any of these exotic objects. We have not identified a neutron star, whose properties can only be explained by a quark or strange matter core. The evidence remains ambiguous. Some neutron star observations are consistent with exotic cores. Others are consistent with conventional neutron matter. The data do not yet force us to choose. The most promising path forward is precise simultaneous measurement of a neutron star's mass and radius. Different interior compositions predict different relationships between these two quantities. A neutron star made of conventional nuclear matter follows one curve on a mass versus radius diagram. One harboring a quark core follows a different curve. Missions like the Neutron Star Interior Composition Explorer aboard the International Space Station are actively mapping this relationship, star by star. This is not a failure of science, it is a reflection of how genuinely difficult the problem is. We are trying to determine the composition of matter at densities that cannot be recreated in any laboratory on Earth, inside objects that are light years away, shielded beneath crusts we cannot penetrate. The tools available to us, mass and radius measurements, cooling curves, and gravitational wave signatures, are indirect. They constrain the possibilities rather than providing a direct image of the interior. Progress is being made. Every new neutron star mass measurement, every new radius estimate from X-ray observations, every gravitational wave detection from a merger narrows the range of viable models. But we are not yet at the point where we can open a neutron star and look inside. What we can say is this: whether the core is made of neutrons, quarks, strange matter, or some combination, the objects we observe behave in ways that are consistent with the categories we have explored throughout this journey. The external behavior, the pulsing, the bursting, the accreting, the spinning is governed by the properties we have discussed: spin, magnetic field, temperature, and environment. The internal composition certainly affects these properties. influencing how fast a neutron star can spin, how massive it can be, and how quickly it cools. But the classification framework we have built, the landscape of types and transitions, does not depend on resolving the internal composition question. Whatever neutron stars are made of on the inside, they still follow the same evolutionary pathways we have traced. And those pathways are worth reviewing one final time, because the connections between the categories are the real story of this journey. A massive star dies, its core collapses. A neutron star is born with a particular mass, spin, temperature, and magnetic field. If the spin and magnetic field are strong enough and the geometry is favorable, it appears as a young, rotation-powered radio pulsar, beaming radiation across the galaxy. Over millions of years, it spins down. Its beams weaken. It crosses the death line and fades into the quiet population of cooling neutron stars, invisible to most instruments. But if the neutron star was born with an extraordinarily powerful magnetic field, it might spend its first few thousand years as a magnetar, erupting with bursts and flares powered by magnetic field decay. As the field weakens over millennia, the eruptions become less frequent and less energetic. The magnetar calms. If its residual field and spin rate are right, it might transition into a high magnetic field radio pulsar for a while, straddling the boundary between the two categories. Eventually, even that activity fades, and it joins the silent majority, or consider a different path. A neutron star in a binary system accretes matter from a companion. The accreting gas produces intense X-ray emission, making it an X-ray pulsar powered by gravitational energy rather than rotation. Over millions or billions of years, the angular momentum delivered by the accreting gas spins the neutron star up to hundreds of rotations per second. When accretion eventually ceases, the neutron star emerges as a millisecond pulsar, a recycled object given a second life. Its weak magnetic field and extraordinary spin stability make it one of the most precise clocks in the cosmos, useful for detecting gravitational waves, testing general relativity, and probing the interstellar medium, or consider the transitional system. A neutron star in a binary hovers at the boundary between accretion-powered and rotation-powered states. When the companion feeds it enough gas, it shines as an X-ray source. When the gas supply dips, the accretion disk is pushed back, and the neutron star switches on as a radio millisecond pulsar. It flickers between categories on timescales of weeks, proving that the labels describe circumstances, not essences, or consider the most dramatic path of all. Two neutron stars in a tight binary spiral inward over millions of years, radiating gravitational waves, losing orbital energy, drawing closer and closer until they finally collide. The merger produces a burst of gravitational waves, a flash of gamma rays, and a kilonova that forges gold, platinum, and uranium. At the center, a brief, furious remnant exists for a fraction of a second or a few seconds. A hypermassive or supramassive neutron star spinning at nearly its breaking point, hotter and denser than anything else in the universe at that moment. And then, in most cases, it collapses into a black hole, ending the neutron star story entirely and beginning a different story altogether. Every one of these pathways involves the same fundamental kind of object. A ball of matter roughly 12 miles across, with a mass between about 1.5 and 2 times the mass of our Sun, supported against gravitational collapse by the quantum mechanical resistance of its constituent particles. The differences between a pulsar, a magnetar, an X-ray source, A millisecond pulsar and a merger remnant are not differences of essence. They are differences of state, spin rate, magnetic field strength and geometry, temperature, the presence or absence of a companion, the availability of accreting matter, the accident of whether the object's beams happen to point toward Earth. This is perhaps the deepest lesson of neutron star science. Classification in astronomy is often about us, about what we observe and how we observe it, as much as it is about the objects themselves. A neutron star does not know what category it belongs to. It simply exists, governed by the laws of physics, responding to the conditions it finds itself in. It spins because angular momentum was conserved during its birth. It radiates because its magnetic field and rotation create the right conditions. It erupts because magnetic stresses exceed the strength of its crust. It accretes because a companion overflows its Roche lobe. It merges because gravitational waves steal energy from a decaying orbit. None of these behaviors define what the neutron star is. They describe what it is doing. And what it is doing can change. The 12 or so categories we've explored tonight are not 12 separate species in a cosmic zoo. They are 12 windows into the same extraordinary physics. 12 angles from which to view the same fundamental object. Each window reveals something different. The pulsar window shows us relativistic plasma physics and precision timing. The magnetar window shows us the strongest magnetic fields in the universe. The accreting system window shows us how matter behaves as it falls into extreme gravitational wells. The merger window shows us gravitational wave physics and the origin of heavy elements. Together, these windows give us a composite picture of what neutron stars are and what they can do. A picture far richer and more interconnected than any single category could provide on its own. And the picture is still being painted. New categories may yet be discovered. Old categories may be refined, split, or merged as observations improve. Transitional objects that defy easy classification, will continue to challenge our frameworks and force us to think more carefully about what the labels really mean. That is how science works. The categories are tools for understanding, not permanent truths carved in stone. They evolve as our knowledge evolves. What does not change is the astonishing nature of the objects themselves. A neutron star is the densest stable object in the known universe. It packs more mass than our sun into a sphere you could drive across in 20 minutes. Its surface gravity would crush you into a film of atoms. Its magnetic field would disrupt your body's chemistry from millions of miles away. Its interior may contain forms of matter that exist nowhere else, states of matter so exotic that our best theories can only approximate their behavior. And despite all of this extremity, neutron stars are not rare. There are roughly 1 billion of them in our galaxy alone. They are everywhere, drifting through the Milky Way, spinning, cooling, occasionally erupting, occasionally accreting, occasionally merging. Most are invisible to us, members of the quiet majority that have faded beyond our ability to detect. But a precious few, the ones we can see, the pulsars and magnetars and X-ray sources and merger remnants, serve as laboratories for physics that cannot be studied in any other way. The next time you look up at the night sky, remember that scattered among the stars you see are objects so extreme, so dense, so powerful that they challenge the very limits of our understanding. You cannot see them with your eyes. They are too small, too faint, too distant, but they are there, spinning, cooling, occasionally screaming across the electromagnetic spectrum with bursts of energy that outshine entire galaxies. They are the universe's most versatile performers, capable of appearing as steady lighthouses, as violent eruptors, as quiet embers, as resurrected clocks, and as brief, blazing remnants of cosmic collisions. They are all the same object, born in the same kind of event, made of the same impossibly dense material. And the reason they look so different from one another is not that nature made different kinds of neutron stars. It is that nature gave the same kind of neutron star an extraordinary range of circumstances in which to exist. Neutron star type is not a birth certificate. It is a weather report. It tells you what the object is doing right now, under the conditions it currently faces, at this particular moment in its billions of years long existence. Change the conditions, and you change the type. Wait long enough, and the type changes on its own. The only permanent thing about a neutron star is the neutron star itself, a tiny, impossibly dense remnant of a dead star, carrying within it some of the most extreme physics the universe has to offer, wearing whatever face its current circumstances demand. And that is what makes neutron stars one of the richest, most fascinating, and most humbling subjects in all of science. Not any single type, not any single discovery, but the breathtaking realization that one object, born in one kind of catastrophe, can become so many different things, can teach us so many different lessons, and can surprise us in so many different ways simply by spinning a little faster, or carrying a slightly stronger magnetic field, or finding itself in the company of a generous companion willing to share its matter across the void. Thank you for joining me on this journey through every major type of neutron star. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep dives into the most extraordinary objects the universe has to offer. Sleep well tonight, knowing that somewhere out there, a neutron star is spinning. And depending on its spin, its field, its age, and its company, it could be almost anything. Good night.